All right, hi. Sorry for the change in the title. I figured this was a bit shorter than what's in the program. So let's get the obligatory out of the way. I'm Leland McInnes. I'm with the Tut Institute. I'm a mathematician and researcher there. It's an Institute for Mathematics and Computing in Ottawa, Canada. And you can get a hold of me on Gmail if you need. So what is clustering is probably a good place to start. So it's about finding groups of data that are similar. So note that I've put scare quotes on similar there. That's because it is a fuzzy notion and it's not as well defined as we might like. So it's also very easy in theory. You just find the groups of data that are similar. How hard can it be? It's very hard in practice. So what does similar mean is really the start of the question we're going to have here. So what do you expect from a clustering? Is it always the same sort of thing, depending on what you want to do? The human eye is really good at clustering in 2D. So I'm going to work with some 2D data, which isn't what most people will want to cluster. They'll want to have higher dimensional data. But we can see what's going on, and your eye can do the job of doing the clustering for you. So you've all been staring at this for a little while. You've probably already, with your eyes, picked out where the clusters are, and you know what they look like. That's great. So the question is, what do clustering algorithms do on this? So let's start with the standby that everyone's going to use first up for clustering, k-means. That's what k-means does to that data. Not quite the clusters we were expecting, I think. So what happens here, k-means tries to find centroids that sort of minimize intra-cluster distance. So it ends up basically assuming that your clusters are going to be Gaussian balls rather than anything else. They have to be like perfectly spherical balls. The other catch with k-means, you have to know how many clusters there are to start with. That's a parameter to the algorithm. All right, what else have we got? Affinity propagation. It looks just as bad, and to be honest, I'm not going to say much about affinity propagation. Agglomerative clustering. So this builds up a hierarchical sort of tree of clusters. There's many methods for defining how to split a cluster to build that tree. What you're looking at here is ward clustering. And then if you cut the tree at a given level, you get a flat clustering, which is what's displayed here. In this case, I told it to cut the tree in such a way to give me 6 clusters. Birch is a slightly different approach at hierarchical clustering. It's optimized for speed. Again, still probably not the clusters you were looking for. Spectral clustering. This uses linear algebra techniques to try and embed the data in a slightly different space. So it has the ability to do a little bit of manifold learning style things, but in the end, usually spectral clustering uses k-means at the end, so you have to have Gaussian balls in your transformed space. Still kind of hard, and you still have to tell it how many clusters you have at the outset. Mean shift is an algorithm that's supposed to handle noisy data. In this case, that data has been colored black. It declared that data as noise and not in any cluster. That's definitely a strength, but it's still centroid-based like k-means, and so it still runs into some of the same troubles. HDBSCAN is a density-based clustering algorithm, and so it tries to find regions of the space that are dense, separated from the other regions of the space. Again, it supports the notion of noise, data that's not in any cluster. Again, it's colored black here. It's better, but it's not exactly there. So what makes this so hard? Because really, we were staring at the data. I could do it by eye. What do we have to do to get clustering algorithms to get there? Well, the big problem actually is figuring out what makes a clustering good. We were looking at 2D data. You could do it by eye. You could see the clusters. But as soon as you're in higher dimensions, you need some sort of measure to tell you whether a clustering is good. And there are a lot of measures. You can worry about intra-cluster separation, intra-cluster homogeneity, representation by centroids, uniform cluster sizes, high-density regions without intra-cluster gaps. There's a whole slew of measures for what makes a good clustering, and in fact, there are probably about as many measures of goodness as there are clustering algorithms. There's a great talk by Christian Hennig at PyData London. You should go and watch that. He covers all of this in far more detail than I can get into and does a fabulous job of it. The catch is that there are so many different ways to capture a different notion of what a cluster means that it's really hard to have one answer for everything. Different applications need a different notion of cluster, so you have to be careful. So just as an example, and I stole this from Christian Henig's talk, which is a better clustering? Here's a clustering of this data into 3 clusters. If what you are trying to optimize for is intra-cluster homogeneity, this is optimal. Here's a different clustering. Personally, I like this one better, but to be honest, I've heard people who said they like the first one better. So what you should be asking yourself is, which one do you like better, and importantly, why? What makes that clustering something that you think is a better clustering than the other? So the question we should be asking is, what is a cluster? What do we mean by clustering? So importantly for this talk, what do I mean by a cluster? Because everyone has a different idea, so let's be clear on this. So for my purposes, I tend to use clustering for exploratory data analysis. I want to find interesting regions in my data that I want to explore further, or I want to just get a better intuition of what my data looks like. So I'm using it in an exploratory fashion. So that tends to need a particular notion of clustering. So to define what I'm interested in, let's start by looking at what not to do. So here's k-means. This was bad. This was not what I was looking for. So what went wrong here? Well, the main thing was clusters just aren't necessarily balls. For my purposes, they might be long and stringy or various other shapes. So we need to not fall into that trap. Here's spectral clustering. So if you look in the bottom corner, there's a red cluster down there, and there's a whole spray of points at the bottom of the yellow cluster or at the top in the green cluster. Those points aren't really in those clusters or the red cluster. It's just a cluster of, I don't know, meaningless points. It doesn't look clustered to me. So not every point is in a cluster. Real data has noise. It could be sample error. It could be corrupt data. It could be anything. There's noise in data, so you need to be able to deal with it. So this was the best of the bunch, HDBSCAN. So what was the definition of clustering that it was using? It meant that clusters were dense areas separated by less dense areas. So that's what I mean when I talk about clustering. But you should think hard about what you mean when you want to do clustering for your application. Because depending on what you want clustering to do for you, you might need a different notion of clustering, and that can heavily influence what is a good clustering algorithm for you. So can we be any more specific about this density-based clustering idea? Well, turns out that the answer is yes. There's a wealth of literature on this subject, and you can put together a fairly good definition. A cluster is a connected component of a level set of the probability density function of the underlying and unknown distribution from which the data samples were drawn. What was that? Okay, so let's make this a little easier. We can presume that there's some underlying probability density function for the distribution that we're sampling from. So here I've drawn that as a heat map over the data, and we can see samples are less likely to be drawn from some areas. I can convert that to level sets, contours essentially, which I can draw. I can pick out some particular level sets and ask what the connected parts are. And that's easy enough to see in this case. And I can call those my clusters. So we can put all that together and just watch it go. We get our probability density function, we take our level sets, we pick out some particular level sets, and we call those our clusters, and we're done. So is that process a clustering algorithm? Because to be honest, those look pretty good to me. So the answer is no, because we don't know the probability density function. Which level sets do we choose? Well, I managed to do that by knowing the answer in advance and carefully choosing them by hand, so I cheated. And computationally, that's ridiculously expensive to do. You just can't compute all of that. Not for real data. So when you have a theoretically good idea, but you can't really compute it, you should start asking, well, what can I compute? What can I actually do? So the first step is to locally approximate the density rather than trying to compute it everywhere. So what does HDBSCAN do? HDBSCAN, which works quite well as we saw, draws balls of a given radius about each data point, And if that ball has more than k, that's a parameter to the clustering, k points within it, then I'm going to call that point dense. Otherwise, I'm going to call it sparse. So here I've colored the in red any circles that have k points within them. They're the dense points, and everything else just has the circles that are sparse. All right, but I had to fix a particular radius. We can flip this around and go the other way and say, I'm going to draw a circle of whatever radius I need to enclose k points. And here I've just colored those circles according to how big the radius is. So we have some notion of density here now. If I transfer those colors to the points, that actually looks like a reasonable estimate of the density. The smaller the radius I had to draw, the denser the point was. So we have some way of computing a local estimate for the density at each point. So what about the connected components? Well, the connected components of these level sets, they form a tree. So it's a little hard to explain, but it's easier to see if you just watch it. In 1D, we have this probability density function, and if you steadily lower the density down, you can see new components show up, and then they merge together, and you end up slowly but surely building up a tree. We can do the same thing with their data by having points, and we're going to slowly grow circles of ever-increasing radius about them. And as they grow, once they become dense, I'm going to color them in. And as they meet each other, as we did in the previous example, I'm going to merge the colors together. And you can see actually a tree forming, and slowly, there they go, we're at the root of the tree. So we can watch this go one more time. You can actually see lots of different colors pop up originally, and they slowly all merge together into just a few colors. So we can build up a tree and use an excess of mass type algorithm to select the clusters out. So hopefully the tree is computable in reasonable time, and it's a little optimization game from there to try and extract out which flat clustering is going to be the best. So what does this look like in practice? Well, here's our familiar data set that we've been playing with. This is the tree we get out when we run essentially what I was describing there. It's not a pretty tree. It's rather hard to understand. There are actually lots and lots and lots of little lines there, but they're also densely packed. It all just looks black. So the trick that we're going to play now is that a lot of those splits in that tree are just 1 or 2 points splitting off. You might have noticed that when you were watching the animation. Often it's just 1 point joining a cluster. Well, what we're going to do is have a parameter. We're going to call it minimum cluster size. And whenever less than minimum cluster size points split off, we're going to say that's not a cluster split. That's just some points falling out of an existing cluster. And when we take that process and run it through the tree, it simplifies down. And we get a really simple looking tree. The width of each bar here, as well as the color, represents how many points are in that bar at that particular time. And you know, as you change the value, points drop out. That's what we had in the original tree. But now it's just a single cluster with points dropping out of it instead of these many, many, many branches. So now our excess of mass game that we're going to play, or a little optimization game, is really, I can describe it here as pick out the clusters that are going to give me the most ink on the page, subject to the fact that if I choose a parent, I can't choose any of its children. So you play that game, you get something like this. I've circled out the clusters that we would select out via that technique. Now, in this particular case, there exists a single cut across that tree that would have picked out all those clusters, but there's actually no reason for that to necessarily be the case. This process can end up picking out quite variable density clusters with no single cut that would pick them all. So the resulting clusters of doing that, that's this, which I think is what I was originally looking for. So this is the HDBSCAN clustering algorithm. It was described in 2 papers by Campello, Mulavi, Sander, and Zimic in 2013 and 2015. And it's obviously an algorithm that gives, as far as I'm concerned, excellent results for a clustering. So the next question is, what about performance? I described something that was at least computable, but can I compute it quickly? So the first problem is we don't want to run connected components for each and every possible radius. What's the solution to that? Well, minimum spanning trees can get us there, because now each edge I drop from a minimum spanning tree automatically disconnects components. Next catch, well, the weighted graph I'm going to do here with distances modified a little bit by that density property I was talking about, that's going to be a complete graph. That's going to have n-squared vertices. That's not very useful. I don't really want to have to compute an n-squared algorithm if I can help it. But we can use spatial indexing to compute fewer distances. By spatial indexing, I'm talking about quad trees, KD trees, cover trees, these sorts of algorithms and approaches and data structures. So they're great for neighbor queries. If I want to find the neighbors of a point, I can do it very quickly via these trees. In fact, you can do neighbor queries in order log n time. And if we use Boruvka's algorithm for minimum spanning trees, we can actually change the minimum spanning tree algorithm into essentially a whole lot of neighbor queries. Now, there's some caveats on that, but in practice, those caveats end up turning out to be extra pruning rules you can introduce to your tree search. So in 2010, March, Ram, and Gray published a great paper on the dual tree Boruvka algorithm for computing minimum spanning trees. And for HDBSCAN, we can use a modified version of that and compute minimum spanning trees in order n log n time. So what does performance look like? So along the bottom x-axis here, I have the number of data points we're clustering. And on the vertical axis, the time taken to cluster. So this is a whole slew of different clustering algorithms and implementations. And HDBSCAN is in dark green there. But you can see there's really a few algorithms that are actually managing to scale. So let's take a look just at those. We'll stretch out the scale a little, cluster more data points. And you can see we're getting much better, but HDBSCAN's still down there. It's hard to see what's going on. Let's take a better look. Still in dark green, HDBSCAN. And now you can actually see that, in fact, despite the fact that HDBSCAN is effectively computing dbSCAN for every possible epsilon value in its parameter range, we actually outperform sklearn's dbSCAN implementation. Now, there's some small caveats on that. You need to choose parameters for dbSCAN that force it to actually produce clusters. If you give it a small enough epsilon value, it'll do no work almost instantly. But we could actually outperform dbSCAN itself. So just because I feel like this is an easier way to think about things, how many points can I actually cluster in a reasonable amount of time? If I want to do it interactively, that's, say less than 30 seconds. If I want to do it over coffee, over lunch, overnight. How many points can you cluster? Now, these are ballpark figures, but this gives you a rough order of magnitude of what you can do, which is to say, you can scale to very large data set sizes if needed with this algorithm. So, what do I want you to take away from this talk? First, k-means should not be your first choice for clustering. K-means probably shouldn't be your second choice for clustering either. Think hard about what you mean by cluster before you go and do your clustering. Clustering means different things for different applications, so think hard about what you mean. And while you're thinking, you may as well run HDBSCAN. It'll probably be done, and it's probably what you want anyway. So, thank you. Questions? Yeah. Okay, so the question was, how does performance scale with dimensionality? And that's a good question because it's a little trickier. I'm using spatial indexing, and that doesn't scale so well with dimensionality. I have had little problem scaling with dimensionality up to about 50 to 100 dimensions, but if you're talking really high dimensional data, it's not going to scale well at all on that front. On the other hand, I would suggest that if you have really high dimensional data, you probably need to run some sort of dimension reduction on it in the first place before doing clustering, because for really high dimensional data, distances aren't really going to mean much. Cursive dimensionality and all. Yeah. Fraudulent transaction data. So the question was, do I have any experience with fraudulent transaction data? No, I do not, I'm afraid. Yes.
So I agree that the clustering result looks good, but I'm just curious about whether we do have any physical object underlying this data point, so we can really confirm that this is the best result.
So the question was, the result looked really good for that data set I had. Did that data set actually represent anything? That data set that I showed you represents my experience trying out many different clustering algorithms and finding out why they broke, and then I made one data set that would break all of them. So it was synthetic data designed to basically make anything look bad. And as it happened, this is why I ended up coding up HDBSCAN. It was an algorithm that produced the best possible results for as many different data sets as I could throw at it. I have thrown it at real-world data sets. I can't really discuss those, unfortunately, but it's worked very well for me, and I have high confidence it will work well for you, especially if what you're doing is exploratory data analysis. Oh, yes?
How does this work if you have kind of like varying scale and density for your cluster? So you might have big diffuse clusters over here, because there may be a bunch of small dense clusters in the sort of meta cluster.
Okay, so the question was, how does this work with varying densities? And in fact, that's what this algorithm was designed to be able to handle. It is something DBSCAN doesn't handle very well. If you have a large sparse cluster and then a bunch of tight clusters, at one parameter setting, it'll pick up one thing and glump everything together. If you swap it around, it'll pick out all the little ones, but throw everything else away as noise. It's hard to tune. Whereas part of the point of HDBSCAN is to give you a very small set of parameters to choose from. In fact, you can boil it down to just one, the minimum cluster size. And it will find variable density clusters very well. In fact, that's its main strength. Oh, yep.
So you talk about the performance in ID. What about the cluster quality?
Okay, cluster quality in high dimension is a valid question. I have found it to be pretty good, as I say, in scales up to maybe 50 to 100 dimensions. In really high dimensional data, I have no faith in any clustering algorithm, to be honest, because cursive dimensionality means that all distances are going to look very, very similar, and it's very hard to cluster that in any meaningful way.
Okay, thank you very much.
Thanks.